So in my teaching, I forgot a couple things, and I want to thank Jennifer for helping me to remember that I forgot to say sorry. No, I didn't mean to pick on you. No, I know that sounds bad. I'm sorry. Didn't mean to. I realize that when you sit in this class and you don't know something, it's very, how should I say, humbling, or I have a question, but I love it. I don't know. There's so many things I don't know, so you'll catch me on things, and hopefully you'll realize that it's okay to not know things eventually, and that's why we keep doing what we do. Not just you, Jennifer. But anyway, she reminded me of a couple things to talk about. The log likelihood. We went from likelihood to log likelihood almost like that. One of the nice things about taking the log is we changed the scale, like this likelihood function itself, but we didn't change where the peak happened at. Right? We just basically shifted it. Right? It's like taking that mountain and just moving it up, or actually in this case moving it down. So the peak occurred still where the mean of IQ and the mean of performance happened to be, but the height of the peak was negative 100 and whatever, versus if we had not taken the log, it would have been a really, really tiny number. Scientific notation tiny, like 0.07 to the negative, or times 10 to the negative 30 or something. Really, really tiny. So a lot of times we take the log for that reason, because the computer is hard. There's a lower limit to how many digits we have in the computer. And the closer we work with 0 when we have a likelihood of a very small number, and the more we multiply zeros, the closer we get to that limit. So we'd rather take the log. There's error in the log function, but there's less error to it than it is to doing the likelihood. That's one reason. And the other thing I wanted to talk about, the likelihood versus the log likelihood, we went from, we had the likelihood, which was f of x1 times f of x2 all the way through, right? This is the likelihood itself. The log likelihood was the sum of the logs, log of f of x1 plus log of f of x2. All right. The reason we went from multiple to times is that when you take the log of a product, right? So if you say that, for instance, you have a function, maybe c equals a times b. If you wanted to take the log of c, that would be equal to the log of a plus the log of b. So it takes a product and makes it into a sum of logs. So that's one of the nice functions of the log. I did talk about it bringing down the exponent. That's helpful. I didn't mention this part here. So a property of logarithms, if you're rusty with math, which believe me, I was and I am still to this day, that works. Questions? So by taking the log, we're not cheating. We're actually trying to make the computer work a little easier, make the math work out a little bit easier, and we still find the same result in that we know what the mean or the right value should be. The MLE is still the right MLE. So let's talk about what we get out of ML estimates. There are some useful things we get out of them. One is something called a likelihood ratio test. This was covered in the chapter. A likelihood ratio test is between a pair of models where one model is nested within another. Right? What does it mean? That means if you have model A, say like this right here, this is sort of a model. It's kind of a saturated model, but it's a model. If we all of a sudden went in and tried to put a 0 here for the covariance, if we said, oh, let's test whether or not this covariance is 0. So we would estimate the full model, the saturated model here. Then we would go back and estimate it with a 0 here. We just make the computer put 0 there. Same process of a maximum likelihood works, just there's no parameter goes, it's just fixed at 0. We could then compare which model we prefer using something called a likelihood ratio test. Right? It'll give us, essentially, a test of the hypothesis of the constraint we just put in. What is the likelihood ratio test? You've seen the log likelihood in lavaan before. I know this because I made you go look for it to check your homework when you were building your model. By the way, was that helpful to know where we're going? I hate the idea that you're kind of stabbing in the dark at things. And so much as I can remember, number 1, and get right, number 2, that number's off. So if you try and it's off, you might shoot me an email. Is that the right number? Because sometimes I'm wrong on those. I know I make a lot of mistakes. But anyway, I hope that helps. log likelihood for the null model, you grab that number, you subtract from it the log likelihood from the alternative model, right? The one with the more parameters. The null is the one with fewer parameters. You multiply that number by -2, and you get a number that happens to follow a chi-square distribution. The chi-square distribution has degrees of freedom that are equal to the number of parameters that are different between the two. And that's what you can use to test whether or not you should keep the null model or reject it for the alternative. Yes, ma'am?
You say the null has more parameters?
Null has fewer parameters. Null always has fewer parameters. Right. The null, we're going to have an example here real quick. Here's a deviance test example. This actually comes in handy with the second part of the homework when we start playing around with different models in R. If we treated these data not as multivariate normal, but just like they were one thing, like, well, maybe actually this is this. If we have this one very specific covariance matrix, if I call it R, we'll know why I call it R next week a little bit more. And it really was equal to one common variance times an identity matrix. What do we mean by that? It means this, right here. I believe that the variance of IQ is equal to the variance of job performance. And not only do I believe that, I also believe that the covariance is 0. So I'm saying my two variables have equal variance and are uncorrelated. That's a pretty ridiculous thing to say, since we've seen the values of the variance estimate, but let's imagine we wanted to test and see if that's the case. Maybe this is a hypothesis. And you know who it is. It's not your advisor, but that one crazy member of your committee. You know that one? That's usually my role. They always call them the outside member. It's usually because it's just the crazy member. Right? You know, right? Okay. And so they're like, I think that these variables, they always talk in that voice, I think that these variables are uncorrelated and have the same variance. And you can say, well, you know what, that's a testable hypothesis. That's an empirical question. We have data, we can try to answer it with the data. And so we have these data, we estimate it to look like this. So we would have a mean for each variable, and we would only have one term, one value for the covariance matrix. So 3 parameters. And as opposed to an alternative where everything's been estimated. Right? So we have a mean for each variable, a variance for each variable, and a covariance. So 5 versus 3. So we could get a log likelihood for this first model, a log likelihood for the second model, take -2 times the difference, that thing's chi-square. If we look it up against the chi-square table, with the difference in parameters being 2, 5 versus 3, we'd have an answer as to whether or not we would reject this null model. All right? And here you have it. Step 1, estimate your null model and get the log likelihood. I have the lavaan syntax in there. This might be helpful for homework part 2, right up here. If you want to constrain a variance to be equal, you have to give it what's called a label. Okay. So what I take IQ and the double tilde, the double tilde that you see here, right there, says I want to do the variance of IQ with itself. That's a little, what's that? It's like an empty model. And then I take job performance with itself, but the term that's out in front of them, var1, is like saying anything where you see var1 times, that's the same value for these. Right? So it equates them to be equal. So if I do that, you'll see in the output for the parameters, you'll see that label var1 again. That's the label I gave it. It's like one variance. That's why I'm calling it var1. You can call it whatever you want. You can call it Templin crazy. Crazy T. Crazy T, crazy Templin. I like that, right? That's who I'm going to be. I mean, I am already, but I mean, my trajectory is like, I know those of you in EPSY, you can go ahead and map me on to some of the elder statesmen of our department. Which one am I going to be? Right? Anyway, so long as they don't kick me out. That's I do have tenure, but I don't take it for granted. Anyway, step 2. So here, these are the estimates. You'll notice here the means don't change. Isn't that cool? We changed the variance, but the means didn't change. There's a reason for that. talk about later. Step 2 is to estimate the alternative model. This is the full model, saturated. You have the syntax from that before. You have all of our estimates. And now, because of that, we know from model 1 there were 3 free parameters. Model 2 there were 5. Remember, free parameters, those are dimensions of the likelihood that it's trying to search over for. We have the log likelihood. It says it right here, user model H0. What? That's weird. User model. H0 is your log likelihood. Then they tell you an unrestricted model H1. Okay, the top you see the 2 difference there. Let's hold off here. My user model, that's what I just ran. That's my log likelihood. That's where the peak happens to be. Let's go down here to the other model. Oh, negative 124.939. I believe that's the number that I found in R when I did the grid search. So it's coming up the same number. But take a look. It matches the unrestricted model. Not only does it match it there, it matches it up top. And this is what I was telling you. The saturated model, this full parameters, it gets estimated every time you run a model in lavaan. Right? It says, oh, you want multivariate normal? What would it be like if I estimated everything there was to estimate in a multivariate normal? And gets the log likelihood. Because everything gets compared to it. So, we have 2 constraints here. We assumed that the variances were equal to some common variance, and that the covariance was equal to 0, and those form the null hypothesis. We could take the likelihood ratio test, which is negative 2 times the difference in these things. It's 47.124. I did that by calculation with R. 2 degrees of freedom. I could look up in the d-norm function, or get this. This is where R exceeds in its usability. If you're using M+, you'd have to do this in separate files, drag the numbers down, and use some other program to compute it. In R, there's a function built in that will do the likelihood ratio test for you between two models. Right? So I called my first model model 01.fit, and my second model model 02.fit. And I use a function called ANOVA. Now clearly this is not ANOVA, but that's an R function that has a big umbrella. Put them both in there, and it says chi-square difference test. There's that 47.124 with 2 degrees of freedom. The p-value is very small. So just like we thought about when we talked about null hypothesis and significance tests, the small p-value there, if it's less than 0.05 or whatever you want to talk about, you would reject. But in this case, you'd be rejecting your null model. Right? Technically, the constraints you put in. But since you're comparing null versus alternative, you're saying that the alternative model is preferred. So if you know that crazy person on your committee thought that you should have equal variances for your variables and no covariance, you'd say, well, that's not the case. The evidence suggests that model is rejected, does not fit. So that is a property of maximum likelihood estimates. Right? This is the analog to the R-squared change test. If you remember linear regression, you'd add a variable, you want to know if you want to keep it. Right? That is a nested model. Right? The alternative model is the one with the added variable in it. The null is the one without. It's like saying whether that beta weight's equal to 0. But the likelihood ratio test, believe it or not, works for any type of model that you have, so long as it's nested and estimated with maximum likelihood. You want to compare the fit? Let's just, in my program, we do a lot of measurement, item response theory. So those of you who don't know these words, don't worry about it. Those of you in our program, if you wanted to compare the fit of a 1-parameter logistic model, a Roche model, and what's called a Roche model, with a 2-parameter logistic model, you can use a likelihood ratio test that works the same way with maximum likelihood. So that's one of the things you get with ML. You learn that, it goes forever. I think that's pretty cool. It's one of the properties of ML. Questions? Next week is all about trying out different models and why we would try them and what it means. Next week is kind of the beginning of path analysis. It really is modeling. This week's kind of maximum likelihood. Next week is modeling. And the week after that, it's modeling on steroids. So. Next thing we get, Wald tests. I've been calling the Wald test the parameter divided by its standard error. We get this in output from lavaan. If I go back a few slides, right here where it says z-value, that is the parameter estimate divided by its standard error. That thing is called a Wald test. It is testing whether or not that parameter equals 0. That is like your null hypothesis. And I'll call this beta. Beta equals 0. It's essentially one parameter at a time, although you can come up with multivariate versions of it. We usually don't. But it's a z distribution because of maximum likelihood. That is the characteristic. I drew it on the board at first. I said, oh, asymptotically your parameters become normal. If they're normal, if you wanted to test the null hypothesis of something versus 0, it's a z test. Put in your parameter estimate, subtract 0 from it, that's just the parameter estimate, and divide it by its standard error. And that's the Wald test. So this is why we see a z value here. Occasionally in programs, like you have in regression, actually more often than not in regression, you see it called T. That is the finite sample version of it. That is for when your n is not infinity. It's perfectly acceptable. A lot of programs use z. Lavaan does, M+ does, Stata does, for everything. Everything that you see. Most of the parameters this works fine for. Where this starts to get a little iffy is if you have a parameter that you're testing on its boundary. If you're testing whether a variance equals 0. It's kind of an odd thing. Why would you ever do that? There are cases in statistics to do it, but we're going to leave it for right now. Here's a Wald test example. These are all the coefficients. If I wanted to test whether or not the mean of job performance was equal to 0, I would take it estimate divided by standard error. I get 17.1714 and a p-value from it. So that p-value says I reject the null hypothesis that the estimate of its mean is equal to 0. Mean does not equal 0. That comes out of ML too. So it doesn't matter whether you're doing a structural equation modeling, a multi-level model, an item response model. I'm just going to name off models here. You may not have heard of any of them. Or you maybe heard me talk about them. I don't know. Anyone have a favorite model? Waiting for it. Someone's going to say it. Somebody? No. Kate Upton. I'm trying to think. No, I mean statistical model. I don't have any favorite models. Anyway. So, we got likelihood ratio tests. We got Wald tests. These are out of ML. Another thing we can do is the likelihood ratio test. We had to estimate two models, and one had to be nested within the other. If we have a model that is not nested within the other, right? So maybe you add a few parameters in the mean and you subtract a few parameters from the variance. Most of our models are nested, so we don't usually go there. But if you do have a non-nested model, you can compare the fit using something called information criteria. They show up in Lavaan's output, and this is AIC, AKIK, information criterion, Bayesian information criterion, another one. What these numbers work like, each model that you estimate with ML gives you a set of these. In fact, Lavaan gives you 3. And so if you wanted to compare your model with an alternative, you pick one, all right? Say, let's take AIC. Your model was 259.877. The other ones may have been 250. The model with the lowest AIC is the one that you should pick. These functions take the likelihood, the log likelihood, and penalize it, or negative 2 times the log likelihood. Negative 2 times the log likelihood is a special quantity. It's like a chi-square. But they penalize that by the number of parameters that are in the model itself. So it's supposed to downweight. The more parameters you have, the better the higher your log likelihood would be. You'll be more peaked with your data generally. But more parameters is less parsimonious. So this is kind of a parsimony-weighted index. But they are not. They do not succeed in terms of picking models when you have nested models. Likelihood ratio tests are uniformly most powerful. Always use them when you have nested models. Only use AIC and BIC when you don't have nested models. Questions? All right, so that's maximum likelihood, and that assumes that we have multivariate normal data. What if our data aren't quite multivariate normal? Robust maximum likelihood. Robust maximum likelihood is kind of neat. what ends up happening is we estimate using maximum likelihood, but we also estimate what's called a scaling factor. So how far off our likelihood really is, or how not normal it is. And based on that scaling factor, we can adjust our standard errors, and we can adjust our likelihood ratio tests to see whether or not the lack of normality is causing some type of fudge error to our testing. So where this helps is if we have distributions that are more or less kurtotic. That's a weird no. Peaked or flat. Here we go. Remember in early statistics, that was you'd hear the words leptokurtic for a very peaked distribution, or platykurtic for very flat. Remember those words? Yeah. If you have a distribution that's sort of symmetric or normal, but just more peaked or more flat, if your data are in that way, then these robust methods sort of help you from it. Kurtosis is the shape of the distribution, and believe it or not, it's from the Greek word for bulging, or at least that's what I looked it up. So bulging being peaked or flat. Flat. I don't know. Flat. I don't know if there's a bulge in flat, but peaked it is. So if you end up having leptokurtic data, so very peaked data, it's too flat or too fat of the tails, you get a chi-square that goes up, so that likelihood ratio test gets inflated. And your standard errors of your estimates are actually too small. Right? So again, these are bad things because it's more likely that you'll make errors in your hypothesis test, type 1 errors or type 2 errors or whatever. Alternatively, if you have platykurtic data, your chi-square is too small and your standard errors are too large. So what robust maximum likelihood does is adjust your chi-square and adjust your standard errors based on how platykurtic your data happen to be in the analysis. Questions? So here's some pictures of kurtotic distributions, again from my favorite website, Wikipedia. I just sit on Wikipedia every night. It's pretty much, Wikipedia is almost like my best friend. She and I go way back. I don't know. And what we're going to do for the rest of the class, we're going to use MLR. And the reason for that is maximum likelihood robust, is that if you have perfectly normal data, there will be no adjustment to anything. Right? So in the best case scenario, you get the same thing you would otherwise if you do it up to this point. But if you don't have normal data, it kind of gives you an insurance to say, okay, let me see if I can adjust my data for this. So the way it works in that line that you do to call lavaan, the SEM function, you add at the end of it an estimator equals, and in quotes, MLR, for maximum likelihood robust, and it does the rest for you. And everything that we've set up at this point gets done automatically. You don't have to worry about it. Just put MLR in, everything else works as expected. It's pretty nice. Let's see here. I'd just like to demonstrate this here. We have two models. We have the saturated model, right, where we have everything in here. Lavaan calls this the unrestricted model. And we have the independence model, right, from the crazy outside member on your committee who wanted the variables to be uncorrelated and equal variance. Right. So it does not affect our point estimates, but here's what we end up getting under. This is the saturated model under MLR. You'll see that it actually tells you in two columns of data what would happen if you did ML and what would happen if you did MLR. And if you look at those numbers, they're all identical. Okay. That doesn't sound good. Oh no, that's a plow. Go. Get us out of here. But here's where things differ. For each, if you fit a model where, like model 4 is where we take. This is the model with the crazy committee member model, and we go and estimate it under MLR. We end up getting the scaling factor for each of these things, right? The log likelihoods may look the same, but we get the scaling correction factor, and the numbers here indicate whether or not the model itself thinks that there's leptokurtic or platykurtic data. Now the data are the same, but the model differs, and so the index, the scaling constant, comes from the relationship of the model to the data itself. So that's where.
Is the amount after adjusted large difference or?
Not usually. Sometimes if you have really not normal data, it can be big. It can be 4 or 5. But most of the time it's usually right around 1. If you had a number 1 there, it would be identical to normal data.
Is this only related with the kurtosis, or does it check the skewness?
It's generally the kurtosis. I don't know. I have to take a look about the skewness. I don't think it does skewness as much, though. Which is usually the problem. They actually usually have both, right? If you have, especially Likert data, if you said, you know, how many months has it been since you killed somebody, right? Usually people say 0, right? And I mean, it's skewed in terms of, like, or something like that. Sorry, that's a little extreme. The data we're going to have coming up in examples when we get to factor analysis is about pathological gambling. And thankfully, there's not a lot of gamblers out in the pathological gamblers in the population, but you'll see a lot of people who don't endorse items, right? I've lied about the amount I've gambled. You know, lied to my family. Nobody does that. Or at least nobody says they do that. But anyway. So how it works is we have to go and take, remember the likelihood ratio test is the difference between the log likelihoods times -2. We end up rescaling that by something that comes from the output of the model. I'm going to flip through this quick because R does it for you. This is another benefit to R. If you're doing M+, forget about it. R built in. Hey, and it's free. You pay M+ $400 as a student to be able to do this by hand. Yeah, I know. Crazy, right? So all this is math you can follow along, or you can use the ANOVA function. The ANOVA function in R, this is the difference between those two models, but now rescaled based on the MLR result. So before, this chi-square difference was 47 with 2 degrees of freedom. Now it's 107 with 2 degrees of freedom. Right? So it's just, we get the same result in terms of we reject model, the crazy model, but at the same time the values of this change because of the MLR result. So we're going to do this thing where we do MLR, and if you're publishing on this, you say we use robust maximum likelihood in lavaan, and then just do everything as you would normally. And it sort of gives you like an insurance factor. Right? Now, the standard errors and Wald tests change just a little bit. Believe it or not, because we adjust things, I ended up, let's see here. Yeah, you'll see under ML and MLR, the one that changed is this, yeah, that one right there. Most of the other ones are the same. Actually, we have a standard error of IQ here that changed as well. Oh, no, standard errors, sorry. The standard errors of the variances all changed right here.
The p-value also.
Yep, yeah, the p-value changed because when the standard error changes, when you take the Wald test, estimate divided by standard error, you change the ratio. And that causes the z-value to change, which causes the p-value to change. So we will use MLR and forget it. I feel like it's like the crock pot, right? I hate crock pot cooking, by the way. Anyone have a crock pot? I don't know if those of you. Do you like the crock pot? Everybody swears by them. I think my mother, sorry, Mom, don't listen to this. Everything else is wonderful, but she used to cook it, and it was like, oh. All right? It's just terrible, 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 terrible. And so, but, you know, why do you like the crock pot so much? Yeah, set it and forget it, right? Isn't that like one of the names of slogans? That's what we're going to do with MLR. Move forward like it's ML. Right? In fact, I don't even have the details as to how where that constant comes from, and I'm not going to give them to you because of that, but there. So, we are going to use MLR and treat it that way. But in general, when you should use MLR, aside from always, the bigger issue is the assumption that you have about data. And this is something that's going to pop up again and again, particularly when we get to factor analysis. If you've got Likert data, most likely you're doing a factor analysis on it. Even if you've got like a 5-point scale, if you do a CFA, you're going to assume it's normal. Each item has a normal distribution. With 5 points, it's really tenuous at best to think there's they can approximately be normal. Right? The shape has to be just right, and you've got now 5 values. If you have less than 5 points, like if you have binary data, like 0s and 1, you certainly don't have a normal distribution. So where you have enough to call normal is tough. And then there's the place where you have a study and you give a 5-point Likert item out, and people only respond in 2 of the categories. Right? You may think you had 5 points, but you really only have 2. Right? Yeah, you know how this happens, right? And so it's hard to make the normal distributions work. And so when you end up getting, the MLR doesn't necessarily help you in all of those cases. It helps you more when you have continuous data to take the leptokurtic version of it out. That doesn't stop people from trying to use these data using SEM with, Likert data. In fact, it happens almost all the time in the social sciences. And I would say that's the number one thing people critique about factor analysis and SEM methods, is that we make this assumption that the Likert scale is some type of continuum, and really it's tenuous at best. Although you can, once you start to get up to, if you have 5 to 7, let's say, options, you have people in all the options and they follow some nice symmetric distribution, it mostly works the same as normal. It's when you have 5 to 7 options, people only respond to 3 of them, and there's a big pile of people at the bottom that say, no, that's no way, that's not like me. That's when it starts to become a hard part. But we'll see that coming up. Okay, that's MLR. How about missing data? Boy, we're hitting all the fun points now. What about those people who didn't give us job performance? We have 20 minutes. I'm going to make this real quick. There's 3. This is going to be like the quickest missing data ever. If you want more of this, I have lectures on it from multivariate statistics. You can find those. I wouldn't say they're quality, but at least there's more stuff. Or if you go and check out, get a copy of the Craig Enders book. It's fantastic. It's a great read on it, and I feel it's very accessible material. But generally speaking, this is kind of a rough classification of how data can be missing. Missing completely at random. We use the terrible acronym MCAR. That's when literally there is absolute chance that just randomness happens. Like for instance, if you have a bunch of data and there's an odd random computer glitch that strikes every so often and just zaps one of your data points. It's like flip a coin, and if the coin lands on heads, make something missing. Right? It has absolutely nothing to do with your data. It's just random, right? Or better yet, you mail people surveys, and accidentally, you had a photocopier that stapled the surveys together, and they're supposed to fill out the surveys and mail them back to you. And some of the people that you mailed surveys to didn't get the 4th page, right? But just randomly, it's just the copier just didn't put the 4th page in there or staple it. Right? That's missing completely at random. If you have missing completely at random, anything you do with your data generally is okay, right? Most often what happens, you throw out the data that has missing and you have less of a sample size. Right? But how often do you have missing completely at random? First of all, you never know. But second, it's much more likely that you have a little bit more strict version of missing. Missing at random means the missingness is related to something in your data. So you're sort of using a little detective work can figure it out. This is like our job performance data. Like when we got to the missing at random example, when I pointed at the beginning of the slide, anybody under a 90 IQ didn't have job performance. That was because IQ was related to whether or not it's missing. If below 90, it's gone. If above, it's there, right? So we have essentially a record of why it's missing, and we can deal with that. If you go and treat data like if you have a missing case and delete it, something called listwise deletion, but you're at missing at random, your estimates are biased, right? So if you go and just knock data out and listen, my name is Jonathan and I listwise delete, right? We're among friends here, right? We're not going to judge. It's missing data anonymous, missing data users anonymous. I don't know. That the listwise deletion only works the way you want it to if that completely random process did something to the data. But if it's related to something in the data, then that listwise deletion is going to knock out some of the people where that data is informative for. So you get a bias. You get a bias. You also get a bias of the estimate. You also bias how much error there is. You think you're a lot more precise. All right, then there's this third category, missing not at random. And there's a really intricate way that data are missing related to what you have or haven't collected itself. Maybe the variable, like you have no information. And in getting out of the last one is almost impossible. So the take-home point in maximum likelihood is when you use it, you don't need to listwise delete anything. You just put in all the data you have, and it lets you assume your data are missing at random, MAR. So that second level of okayness, right? Which is a little bit more plausible than the first. Right? So if you use least squares or you use something where that automatically listwise deletes, it knocks you back down and you may have bias. But use maximum likelihood and MAR happens. Here, how does it work? Here's how it works. Uh-oh. Did I really just do that? Are you kidding, template? Okay. Here's how it works. If we have, here's our data, here's our model, saturated model. Remember the log likelihood, right? There's a function called DM norm, right? This is for a person that has both IQ and performance. What happens when you get in the algorithm and you have a person that only gave you IQ? All right? Well, it says, okay, fine. I'm not going to use a multivariate normal for that person. I'll just go use the terms that formed a univariate normal for them. Like that. And I'll just enter in that one observation, the mean of that observation, the variance of that, into my likelihood. So, okay, I didn't throw out IQ. I still kept it. So sure enough, it uses all the data you have. It just essentially resizes the multivariate normal to work. That's almost too easy, right? I mean, it's not easy, but when you get down to there, it's like, oh, you mean we're just going to go and say, oh, that didn't exist in the first place? Okay. And believe it, doing that lets you assume you're missing at random because you're able to keep perhaps the variable in the analysis that might be causing the missingness in the first place. Right? So everybody who's in this analysis who just gave you IQ will still give you IQ, which means your analysis will give you a better mean for IQ. It may not help you much on job performance, but it does help. So they just skip over it. That's it. Amazing. I came up with that as a grad. I mean, like, I didn't understand missing data, but I had a problem where I had some of it, and I built a likelihood. Oh, yeah, I just ignored that part. Oh, yeah, that's what it's doing. Yeah, just ignore it. Don't worry about it. It's like, wow, really? Yeah, really. Okay, so one thing that you'll see, how we get over it, you may hear people talk about we want to impute missing data. We want to kind of, sorry. There are lots of ways around it. Well, this last one is a lot of kind of fairly popular, particularly on this campus. We had a lot of people run around going, I want to impute data. Imputing data is, oh, it's missing, but I'm going to go plug in a value for it, right? So think of it this way. That missing data, you're making it up. Right? You may have a nice educated guess for it, but you're going to make it up. Wouldn't it be great if you could make up all of your data? That'd be awesome. Yeah. And here's the question I have. Do you have to go to IRB for those missing people that you made up their data for? Right? But what imputation does is it uses a statistical model, usually the saturated model, and it says, oh, you don't have performance. Okay, well, I know that from the saturated model that the estimate of performance is correlated with IQ, and so therefore I can form a regression and kind of predict what your value is, and you go and plug in a value with some error to it, some random value from that distribution. And then you run the analysis, the full analysis with these random values. But then you repeat that process. Plug in a value, run the analysis. Right? And you end up with a ton of repeated analyses. And those repeated analyses then you cull together to come up with your point estimates for all of it. If the imputation, if you do it right, should lead you to the ML result if you can get it. Right? That's the short of it. I know this is like literally a 10-minute discussion of missing data. In my multivariate class, I like to have a lecture and a half on this if I can. And you can actually teach a whole class on this if you really wanted to. But this is woefully short. I'm trying to hit the high point. But the goal in this class, and for most of the things we're going to do in this class, we don't need to touch imputation because we'll do it. Maximum likelihood will lead to the same result anyway. All right. Okay, so these are the questions. What's maximum likelihood? An estimation process. Find the peak. What's robust maximum likelihood? Well, if you don't have normal, rescale it. Why use ML or robust ML? Good properties. Can trust them. The estimator you can trust. I sound like a politician now. What additional hypothesis tests do they provide? Likelihood ratio tests. Wald tests. Ironically, likelihood ratio tests answered the quiz question. How many models do you have to estimate? 2. Wald test, how many models do you have to estimate? 1. You have to estimate the alternative model, right? The one with more parameters, and see if the parameter is 0. Okay, so we've covered 2, null and alternative. We've covered alternative all by itself. Believe it or not, there's one where you can estimate the model that's the null and get a hypothesis test. Those are called score tests. I didn't talk about them today, but they're part of ML as well. They're really amazing. Oh, you mean that you didn't put that in there, but I'm going to use ML and guess what it should have been had you added it. And then guess whether or not you should have added it using a likelihood ratio, what the likelihood ratio test would be for it. Right? We use those in structural equation modeling. I didn't talk about them today. They're called score tests in statistics. They've been around since like the 1940s. In structural equation modeling, we have a term for them called modification indices, or mod indices. And they literally say, oh, did you leave a parameter out? Let's see what would happen if we were to add it into the model. Without having to estimate the model, it's all based on the likelihood function again. Pretty amazing. Anyway. And finally, how are missing data handled? You know a person doesn't know statistics, or, well, when they use the word handle, but I hate the word handle. Oh, yeah. Oh, it's handled or controlled for or whatever, but yeah. It's just skipped. That's how it is, right? So let's talk homework real quick, because I want to, so a couple things. Number one, I'm going to, those of you who submitted homework this week, I'm grading them most likely tomorrow morning. If not, then Friday morning. And I will send it back to you. You have the chance to fix the things that were not correct. You just need to submit those corrections by next Wednesday at class, right? So fix them, get it all straightened out. It should be fine. So you can get 100% even if you didn't get 100% this time. Number two, homework number 2 is due 2 weeks from today. So you have 2 weeks to work on it. And I strongly encourage you to start, because this is a homework that's a little bit, again, obscure. I have 2 parts. The first part wants you to take only flowers. There's a data set I'm going to give you. You can actually, a data set that's downloadable. This is a very famous data set. It's called Fisher, like, you know, the guy who did the F test. Fisher's iris data. And Fisher was so awesome, he measured petal lengths, petal widths, and then something called sepal lengths and sepal widths as 3 species of iris flowers. Have you ever heard this data before? Maybe those of you in multivariate. Yeah, you have? Wow, cool. A lot of times it shows up for cluster analysis. If we want to go and say we didn't know what species it is, can we figure out what it is if we just observe the data? Or discriminant analysis. But anyway, this is what it is. I want you to take some of these data and give me multivariate normal, give you the saturated model for just 5 observations. So it's just 5. But then I want you to give plot the PDF using the denorm function in R. This is, if you take the syntax from the graphs today, you'll find out how to do that. And then I also would like you to report the univariate normal log likelihood, right, for each measurement. Right, so you got 4 observations per flower, 2 widths and 2 lengths. You plug in the mean and variance for each into the denorm function. It gives you the log likelihood. Right? Finally, I want you to do the DM norm function, the multivariate normal, right? Using the mean vector and the covariance matrix for each observation, figure out the height. And the last question is sum all those together. And the irony is what you did to start this question, which was use lavaan to give you the mean and mean vector and covariance matrix of these flowers. If you do all these questions right, number 5 will be equal to the log likelihood that you get from number 1. Okay. So basically, I want you to sort of recreate what lavaan's doing with these two functions in R. Right? It's not by hand; it's all in R. And using the first part of my R output that had the D norm function, the DM norm function. So now I'm not going to lie, that is a little bit challenging, it's a little bit esoteric, but I want you to do that because I want you to see, I want you to think about what's coming up. You're getting these heights, what's going into the numbers to give you the heights. I feel like with that knowledge, you get a little bit higher ceiling to the models that you do as you go through statistics, and in particular R class. Part 2 is to estimate 4 different models in lavaan, and this might help after class next week, but in this homework and with class today, you should be fine. One model has equal variance. By the way, there's the model syntax for it. All right, one model has equal covariances. There's the model syntax for it. Then one has an equal means. That's the model syntax for it. So I try to give you the model syntax for each of these 4 models, and I want you to do these 4 models with all of the data using robust ML, so you can check this. And at the end of that, answer a few questions about it. So what's your estimates? Do a likelihood ratio test, and then kind of do these numbers change or do they not change? Now, but these models, you'll have 4 bits of syntax for each, one bit of syntax for each model, and then one lavaan statement. You'll be able to do the likelihood ratio test with that ANOVA command. So believe it or not, everything that is able to do this homework with has been talked about today, but I strongly implore you to start soon with DNorm and DM norm, because those things take a while, just because you've got to structure the data into, well, it comes in matrices, but you can see with my code, try to follow along with it. Questions?
Is there any missing data in there?
No missing data. All complete. All complete. I will warn you when we get into data that are missing, but I haven't made the third homework yet. That'll be path analysis, but there may be some missing, but I'll warn you and talk about how to handle it. Bring it in. Other questions? Yes, Megan.
For the first one, what are you putting in to get the mean vector for? All of them?
No, you want to just use the observations 6 through 10. So if you look at this data set, there's 150 observations in it total.
But where do you find the means for?
The means for the 4 variables from observations 6 through 10.
Okay.
So what you have in the data set are 150 flowers, 4 quantitative variables: sepal width, sepal length, petal width, petal length. 4 measurements for each flower.
5.
No, 150 flowers, yeah, and you'll get 5. You'll have 5. The first question asks you for 5 of those flowers. Flowers 6, 7, 8, 9, and 10.
Okay.
I'm doing that because it's something where you can kind of dissect it and take a look at the height, what goes into the bigger likelihood itself. Am I scaring you? Does everybody look scared? Don't be scared. We'll do this, and you'll be a changed person forever. Have a good evening, everybody. Drive safe.